Hi, everyone. My name is Özgür Yılmaz. I'm the director of PIMS, the Pacific Institute for the Mathematical Sciences, and I'm delighted to welcome all of you to today's invited address by Professor Wilfrid Gangbo. I wanted to just kind of advertise our institutes. This session is sponsored by 3 prominent math institutes in Canada. PIMS, my institute, it's headquartered at UBC, CRM in Montreal, and ARMS, Atlantic Association for Research in the Mathematical Sciences, which is in the Atlantic Canada. With that, I'm really happy to be here, and I'm going to pass it to Professor Shoumik Pal to introduce our speaker today.
All right, thank you, Özgür. Thank you, everyone, for coming today morning. It is my great pleasure to introduce our speaker today, is Professor Wilfrid Gangbo from UCLA for the CRM PIMS ARMS invited address. So Wilfrid's primary research areas are calculus of variations and partial differential equations. He's a pioneer in the theory of optimal transport. His work on the structure of optimal transport plans, for example, the famous Gangbo-McCann theorem from 1996, has played a foundational role in the development of this area over the last 3 decades. I should also say that this paper continues to inspire me every time I still read it. He has also made groundbreaking contributions to the multi-marginal optimal transport theory and to the theory of optimal transport with L1 costs. More recently, his work has focused on developing the theory of Hamilton-Jacobi equations and related equations in the space of probability measures and applications to mean field games. Wilfrid is a member of the American Academy of Arts and Sciences, fellow of the American Math Society. He was awarded the 2018-19 Chancellor Professorship by the Mathematics Department at UC Berkeley. Among his notable services to the math community, Wilfrid was a program director at the National Science Foundation from 2012 to 13. He has been an associate editor for numerous international journals and served in the advisory boards of various institutions. I also particularly want to mention his work with Professor Nelson and Coleman when they launched the David Blackwell Summer Research Institute in 2021, which is named after the famed statistician. This is a 6-week elite research program for undergraduate students, which aims to honor Blackwell's legacy by attempting to increase the number of students who aspire to achieve the kind of excellence and widen participation of African Americans in obtaining PhDs in mathematics. We are greatly honored to have him speak today. Wilfrid.
Pleasure to be invited to give this talk. My talk is based on a joint work with David Jekyll, who is here in the audience, Nam, and Aaron Palmer. So I am going to start with some consideration from the calculus of variation, because I want to spend more time motivating why we start working on a certain set, and then we have to look at a quotient space. So one of the greatest challenges in nonlinear PD, if you are doing elliptic or parabolic PD, the main problem is assume you have a function f defined on a topological space, and assume you are looking for decide whether or not the function admits a minimizer. So you take a minimizing sequence, and you hope that you can find a topology such that this sequence will converge to a certain limit, and you will wonder if this S infinity will be a minimizer. So as you can guess, the answer to this question in general is no. Sometimes you have, often you have some kind of convexity condition, which will ensure you that your function has a minimizer. But it will often happen that you have no convexity structure. In this case, if you have some invariance property, you may hope to find a minimizer. And with this invariant property, you may be able to introduce a quotient topology. And this quotient topology will have a stronger compactness property than the original topology. So for this audience, I want to go through something which we are very familiar with, which is the optimal mass transport theory. But my talk will not be about optimal transport. It is just to describe how it fits in this setting. So assume that you have a Hilbert space, which is the set of maps from the cube to RD. And for simplicity, let us take the closed ball of radius R, but the closed ball in the L infinity norm. And I am going to take a very simple function. This is the simplest function I can think of if I don't impose the function to be linear. Denote by x. So for every x, which is in the Hilbert space, I denote by s by law of s. The push forward of, I take the Lebesgue measure on this set. I push forward the Lebesgue measure to RD. And it gives me a probability measure, which is the law of x. I am going to define an equivalent relation on S as follows. S is equivalent to y if and only if the law of x equal to the law of y. Let me write this differently. Let us denote by R, S1 to SD, the set of commutative polynomials with real coefficients. This previous statement which I wrote, S is equivalent to Y if and only if, when you integrate any polynomial with respect to the law of x, you get the same thing as when you integrate a polynomial with respect to the law of y. It is very natural to define the quotient distance this way. If I call bracket x naught the class of equivalence of S naught, and the same thing for the class of equivalence of Y naught, then the distance on the quotient space between these two classes of equivalences is I am going to minimize the norm, the distance between X and Y, where X will be equivalent in the same class of equivalent with S naught, Y will be in the same class of equivalence with Y naught. And you can observe that what I just wrote is the Wasserstein distance between the law of S and the law of Y. So working on a quotient space, I can choose a sequence Sn which has a better structure than if I choose an arbitrary sequence. For instance, I can choose it to be the gradient of a convex function. And convex function has the property that they converge almost everywhere. And if they are bounded, this is enough to give you LP compactness for every P, which is strictly less than 1. So due to that, you are going to prove that S infinity, there exists a limit, which is S infinity. And what I've done here is, in fact, originally, I was given a problem on the Hilbert space. I quotiented the Hilbert space by the set of measures which preserve a Lebesgue measure. I got the set of probability measure. The set of probability measure have good compactness property if I can control that mass. If I take a sequence of probability measure and I can control how the mass goes to infinity, I can control the limits of this sequence of probability measures. So the above remedy, which is proposed here, work well in classical mechanics. And so you can apply the same thing in classical game theory because many classical game theory are based on classical mechanics. In this talk, I'll be interested in reaching the realm of non-commutative game. So here, the order in which you apply your strategy matter. In classical game, if you apply strategy 1 before strategy 2, or you apply strategy 2 before strategy 1, you get the same outcome. But here, the order will matter. So I am going to use this notation. This bracket C S1 to SD we said will be the set of commutative polynomial with complex coefficient. And this angle bracket C S1 to SD will be the set of non-commutative polynomial with complex coefficient. So I want to start with a simple description of classical mechanics. I am then going to go with a little bit more complicated description of classical mechanics before I go to quantum mechanics. So once I do that, the goal of our work is to develop a free non-commutative analog of stochastic control and Hamilton-Jacobi-Bellman equation. So let me start here with classical mechanics. The observables are represented by diagonal matrices, and so with a real coefficient, and so they are self-adjoint. The symmetry group is the permutation group. If you give me these diagonal matrices, D diagonal matrices, I can construct a measure by taking the J column to represent a point in RD, and the average of the Dirac masses concentrated at this point will give me a probability measure. So I have written, if you give me diagonal matrices, a certain number of diagonal matrices, I can convert that into a set of probability measure, to a probability measure. So what happened here is true, even if my matrices are not diagonal. So I started with this example because diagonal matrices commute. So let me look at more general matrices. I assume that I have D self-adjoint matrices, and I assume that they commute. Since they are self-adjoint, if you write M square alpha for any alpha, you get a matrix which is non-negative. You can conclude that if you have any non-negative polynomial, the trace will be greater than or equal to 0. And so the linear map, which to any polynomial with a real coefficient associate the trace applied to, when I apply P to M1 to MD, I get a matrix. I write the trace of that. I will get a non-negative number. And so I have a linear non-negative functional. By the Riesz representation theorem, there exists a Borel measure on RD, which is going to satisfy this relation. If I integrate any polynomial with respect to that Borel measure, it will be equal to the average trace you apply P to M1 to MD. So this is a less direct description of what I did before. When I have diagonal matrices, I can write explicitly what my measure is. Now I go back to the non-commutative case. In the non-commutative case, we are interested in any self-adjoint operator. But I would like to start with a description where we are in finite dimension. And so my self-adjoint operators are represented by matrices. So I am going to take the self-adjoint matrices, and I am going to denote the normalized trace by, I take the regular trace, I divide by n. This is to ensure that when I write the trace of the identity matrix, I get 1 no matter what dimension I am in. And if I want to let n go to infinity, which will be my later goal, I have an object which behave well. So let Un be the set of unitary matrices. I can define an equivalence relation on the set of D tuple of n by n matrices which are self-adjoint. I take the Cartesian product, the D Cartesian product. So M1 to MD will be equivalent to N1 to ND if and only if for each one of the component M alpha, I can write M alpha is U, N alpha U star. And that should be true for every alpha. Now I want to look at something more general. I want to be able to, I want to take Mi to be an N by N matrix, and Ni to be an M by N matrix. So the matrices may not have the same dimension, because later, when I am going to compare operator, decide if operators are equivalent, I want to be able to do it even if the operators are not defined on the same Hilbert space. So it is known that if I take, if M equal to N, the previous relation I wrote can be expressed in terms of the trace. If M is in MND, each component are self-adjoint. If I take N, the component of N are self-adjoint matrices in the set of M by N matrices, then this equivalence relation means that the trace of P applied to M1 to MD equal to the trace of P applied to N1 to ND. Now I can write this relation makes sense even if M is not equal to N. And this is what I have in mind later when I want to define an equivalence relation. I need to be able to have a trace. I am going to take a set of a subset of a set of bounded operators in Hilbert space. If I can find a trace on that subset, and I have a second subset of bounded operator on a Hilbert space, I will be able to compare the law of the element of this set. So we want to interpret the limit when n goes to plus infinity of M and C. So this notation which I am using is very misleading in the following sense. If I look at the particular subset I will be interested in later, which are subset of bounded operator on a Hilbert space, some of them I will not be able to obtain them as a limit of such a set in any reasonable sense. Some of them I may be able to obtain that, but just to guide our intuition, let us assume that we want to take the union of the set of n by n matrices and put them in a bigger set. So I am going to replace C to the n by an arbitrary Hilbert space. I am going to replace the set of n by n matrices with complex entries by the set of bounded operator on the Hilbert space. And I want to replace the trace on the n by n matrices by a trace on the set of bounded operator. If the dimension of my Hilbert space is plus infinity, there is no linear operator from the set of bounded operator to the set of complex number satisfying the threshold property that the trace of AB is the trace of BA for every AB, and the unital property that the trace of the identity matrix is 1. So we will be forced to work with a subset of the set of bounded operator. We are going to impose that we are working with subsets which are closer under the adjoint operation. So if X is in A, the adjoint of X will be in A. We are going to impose that the identity map is also in A. And we are going to assume that A is closed for the weak operator topology. Then we'll need a trace, which is a linear map from A to C. This linear map will be threshold. It will be unital. And it should allow us to define an inner product. So if I compute the trace of A star B, and I define that to be the inner product between A and B, this should have an inner product property. We are going to require that tau is continuous for the strong operator topology. I am going to remain vague about what I mean continuous for the strong operator topology. So it will be continuity using the net and not sequences. When 3i and 4i hold, we call A von Neumann algebra. And when all these properties hold, in this talk, I am going to call A tau a threshold von Neumann algebra, although my definition here may be a little bit different from the definition in some literature, but it will be simpler for my talk to give this name, to call this a threshold von Neumann algebra. So let us assume that we have a threshold von Neumann algebra, and I am going to denote by A self-adjoint the subset of A of self-adjoint element. So this D here as an exponent is a misprint. It should not be here. So it means that an element A of curl A is in this set if A equal to the adjoint of A. When you have a random variable, which are defined from a probability space to RD, you can define the law of this random variable, which is what I did a few minutes ago. Similarly here, we are going to take X, whose component S1 to SD are in the set of self-adjoint element of A. We are going to use that to define a linear function on the set of polynomial, non-commutative polynomial of D variable with complex coefficient. To each polynomial, we are going to associate, we apply the polynomial to the element S1 to SD. With this, we are going to produce another element of A. and we apply the trace to that. So tau A, this tau should be tau A. Now let B be another threshold for Neumann algebra. We are going to say that the S1 to Sn, which is in A to the D self-adjoint, is equivalent to Y1 to Yn, which is in B to the D self-adjoint, if the law of S equal to the law of Y. And this is what I wrote earlier when we were dealing with matrices of different size. You will soon see why I want to set A to be L infinity. I want to identify A with L infinity of A to compare it to what we do classically. So we need a good metric on the union of this set, and even a bigger set than the union of this set. And to get that metric, we are going to rely on a quotient relation. Fortunately, Bern and Voiculescu, they offer such a metric in free probability. So let lambda naught and lambda 1 be two non-commutative laws. For instance, I can start with x naught and S1. So S naught, we have a D component. Each one of the components will be in a Fourier-Newman algebra. Lambda 1 will be lambda S1. S1 will have a D component. Each one of them will be in B, a Fourier-Newman algebra. And I'm going to define the Bian-Voiculescu distance between lambda naught and lambda 1 in a natural way by this quotient distance. So observe that here, I am minimizing over the set of Fourier-Newman algebra. I start with some original Fourier-Newman algebra, but I may be looking for an FOMM in a much larger Fourier-Newman algebra. So if you compare that to classical mechanics, if you have two probability measures, assume that I have an average of Dirac mass in Rd and an average of a second average of Dirac mass in Rd. And I am looking for optimal way to connect these Dirac masses against a cost function, what appear in optimal mass transport theory. If I go to a bigger set, say R2D, and I look for the optimal map in R2D, it will, the optimal plane, sorry. In R2D, the plane will always be in RD. So even if I look in bigger set, I don't go outside my small set. But here, in the non-commutative case, there are examples for which you can use to show that when you increase the size of the set, you can decrease the value, which is going to serve as a metric. So there is a comparison between the Wasserstein metric and this Bian-Voiculescu metric. You remember earlier, I said that if I am dealing with matrices which commute, then I can associate to any D apple of this matrix, I can associate a measure to that. You can check that the second moment of the measure is finite. And in fact, you can check that the measure is of compact support. So Bian-Voiculescu, they show that if my matrix commute, then the distance they propose coincide with the Wasserstein distance between phi m and phi n. So in other words, I can look at classical mechanics from this point of view. I can look at data as a particular case of quantum mechanics, where I am dealing with operator which commute. So next, I want to go to a more familiar world. So what I mean to say is at some point, I tried with various people. I gave this presentation and asked them what they think. And they said that it is too abstract. So what made me really concerned is even some French people said it was too abstract. So what I want to do now is I want to go away from, hope to go away from abstraction, and let us talk about things we are more familiar with. And if you got overwhelmed at some point, you can view this as the beginning of a new talk. So usually when I am teaching a class, I make promises to my students so that they feel comfortable, and later they discover that I was lying. So I want to switch topic. Let us start with a folklore from stochastic analysis and PD. So you have a finite dimensional space, a flat space, or sometimes not a flat space, but let us talk about a flat space to make our description easier. Assume that the dimension of the flat space is M, and I define the Laplacian operator in the standard Laplacian operator. It is well known that it is a generator of M-independent Brownian motion. So I am not going to recall what it means to be a generator. But when I want to solve the heat equation, for instance, I can use this generator to write explicitly the solution. So here is an example. You take the set of n by n matrices. As a real Hilbert space, the dimension is n squared. The Laplacian operator on this set, and whenever I am talking about the Laplacian operator, remember that my trace is, I am using the average trace, 1 divided by n regular trace, and so everything I am going to say will be with respect to that rate. So I am going to rescale appropriately the random path. So I will have a random matrices. This one should not be there. These two things should be the same. And so it means that I fix a probability space, and I fix a filtration which at the moment look out of place because I am not going to use it for a while. It is not going to play a role for a while. You can write explicitly what this random matrix is. It will be a matrix such that the real part and the imaginary part of each entry is a Brownian motion. But a Brownian motion which you are going to scale appropriately, and I'm going to show you what it is in a few minutes. So I want to point out that when you look at the distribution of each one of the entries, the support is unbounded. So I was looking for a picture online of normal distribution, Gaussian measure. It is very difficult to get a picture where the Gaussian is not compactly supported. They all are compactly supported. But of course, here I want to insist, this is the best I could find where you can see that there is still some space between the horizontal line and the Gaussian. So for those who are familiar with it, this is what is called the Gaussian unitary ensemble process. Actually, for t equal to 1, it is the Gaussian unitary ensemble process, and I have made up the name of calling the whole thing the GUE process. The matrices are self-adjoint. Therefore, they are diagonalizable with real value eigenvalues. The eigenvalues are, of course, random. I am going to define this empirical measure. Because the eigenvalues are random, this empirical measure are random. This is a universality result which goes beyond this example. It says that if you take these random matrices, they converge weakly and almost surely to a deterministic measure. And the entries, these are not compactly supported, but the limit will give you something which is compactly supported, and you have this explicit formula. So what I mean is if you take the law of these random matrices, you pass to the limit, you get this probability measure, which is deterministic. And this will hold for every p, which is a polynomial on the real line. So I want to look at a more general example, which will be closer to my interest. So the description I am making, if I take a d equal to 1, then we are in a case I have only one matrix. Everything commutes, right? The matrix is commuting or not commuting. There is no point to that. Everything commutes. And so I am back to classical mechanics. So any description which is made with d equal to 1 is far easier than any description which is made with d equal to 2 or higher. And so I am interested in the case where d is strictly greater than 1. As you can guess, since we find that the Laplacian operator is the generator of a GUE process, you can conclude that the Laplacian operator on the Cartesian product is the generator of D GUE processes. And I am going to use them in my stochastic game on the set of D by D, n by n matrices multiplied by itself d time. So I am going to fix two parameters. If I was in the classical case, this will be a diffusion coefficient, which I am going to put in front of my Brownian motion. But I want Brownian motion to appear in a different way. In a mean field game, which you don't necessarily, I mean, only for those who are familiar with it. In mean field game, we have a common noise and individual noise. So the way to understand that in the classical case, which, I mean, you cannot use a classical description to say what happened in quantum description. So just the classical description is just to tell you what motivates the common noise and the individual noise. So assume that you have a D player. The players are moving, but their movement is affected. There is some randomness in their movement due to their own noise. And then on the other side, you have an institution which want to force people to react to their decision. For instance, if you raise the price of gas, you hope that maybe less people will use gas depending on how much you raise. But this institution, the decision it makes is supposed to have the same impact on all players. And this is a common noise which is applied by one institution to everybody. In a main field game, when you look at, and the analog may be true here, when you look at the free parameter, then it has some smoothness, it's some smoothing effect. When you look at the common parameter, it kind of destroys smoothness. So I am going to take my processes, D of them, GUE processes, and I am going to choose a one-dimensional Brownian motion. Here I have a matrix. I have D matrices, which are random. Here I have a real number, but I can construct a matrix by multiplying the identity by this real number. I am going to take alpha 1 to alpha D, progressively measurable, mean measurable in a certain sense, which I am not going to be more explicit about. And I am going to call this control. It is called control because once I choose my alpha, it is going to determine the path which my observable are going to follow. I will assume that I know the observable at time t0. I have D of them. And I want to decide how they involve. They involve according to this stochastic differential equation. Observe here that I can explicitly write the solution. It will be St equal to S0 plus the integral from 0 to t of alpha s plus W0 t minus W0 t0, and so on. So this is a stochastic differential equation whose solution is explicitly written. Just to realize what is happening, I want to emphasize the following. You have a free individual noise. I have a matrix where all the entries are 0 except the diagonal. Now, in case of the GUI, all the entries, each one of the entries is non-zero. And each one of the entries involve a Brownian motion. Of course, on the diagonal, the Brownian motion are real. Out of the diagonal, the Brownian motion are complex, non-real. And 1 over the square root of 2 is because I want to preserve the norm of this must be equal to the norm of that. And one check that 1 divided by square root of n is a good normalization if you want to see what happens as n go to plus infinity. So when you pass to the limit, this randomness is going to convert to a trivial thing. It will be BF multiplied by the identity in the big space. And this is where you may expect, are you going to be puzzled by what this limit will be? So coming back to the game, I am going to assume that I have a function which I call a Lagrangian for those who are familiar with Hamilton-Jacobi equation, and I have a terminal value. So this is the terminal value associated to the game. I give myself a running cost, and I want to decide what the value of the game will be at each time t. So the value function, you define the value function to be, you take the expectation of the integral from 0 to t naught. You apply the Lagrangian to st alpha. So this plays the role of position in classical mechanics. This plays the role of velocity. You add the terminal value applied to the terminal, what will be the terminal position if you were in classical mechanics, and you compute the expectation. You minimize over alpha, and what you get, it will be the value at time t naught for the observable s naught. And here I wrote explicitly the solution to our stochastic differential equation, which is what I use here. So you want to understand the limit as n goes to infinity of this infimum. It is hopeless to get something unless you require some compactness property. So I am saying that if I will be studying this problem for a very general class of Lagrangian, a very general class of terminal value function, by general, assume that even they are bounded, they are of class C infinity and so on. If you are doing that, there is no hope you can be able to say something about the limit. So what is going to happen here is, with the invariance property, we are going to see that this gives us some compactness property. So my G will satisfy the property that it is well defined on the quotient space, and my L will satisfy the property that it is well defined on the tangent bundle of the quotient space. If I want to understand the limit when n goes to infinity, I should be able to describe LA for each A, which is a von Neumann algebra. So I am going to assume that I have a family of von Neumann algebra, which are going to satisfy a certain property. I need to impose some consistency property. For instance, what this is saying is, assume that I have a Lagrangian defined on the set of n by n matrices. And I look at the Lagrangian defined on the set of m by n matrices, m greater than n. I want to know that in some sense, I have an extension from the smaller set to the bigger set. And the way to say this is, if I have a threshold embedding from A to B, then the Lagrangian on B satisfies this property. When I project it on A, I get LA. So what I said last time was the GUI process are going to convert to a deterministic process. And now, in the case of, in the classical case, you can keep working with a prescribed Brownian motion. You can let the Brownian motion to be free, but it will not matter. Mainly based on the principle that if I take two non-atomic probability space, they are the same. They are isomorphic to one another. And so whether I let my probability space vary or I fix them, it doesn't matter. But in the non-commutative case, this matters a lot. I have to keep track of the phenomenon algebra I am working with. Here is the stochastic differential equation I am going to look at. It looked like the previous stochastic differential equation. This randomness is still there in front of the identity matrix, but this now becomes deterministic. For those doing Hamilton-Jacobi equation, you are tempted to introduce this value function. It will be useful, but the following is a fact. If you let the finite dimensional initial position converge in law, you will not expect, you can show use counterexample to show that this is true. This is not true. The limit of the finite dimensional problem is not what I wrote in the infinite dimensional case. What is rather true, and what is proven by myself, Jekyll, Nam, and Palmer, is assume I take matrices which are bounded in the operator norm independently of n. Assume that I have an element of a phenomenon algebra, and the law of my matrices converge to the law of S0. Then when I compute the limit of the finite dimensional value function, I am going to get a value which is what I wrote above, but I am going to minimize it over the set of phenomenon algebra containing A. When I do this minimization problem, it gives me the invariance property. It tells me that the new function I define is well defined on the quotient space. So the previous function, which was here, no wonder it cannot be the correct function, because this is not a well-defined function on the quotient space. So this is the fourth part of my talk, and I thank you for your attention.